So if we go ahead and look at half-life with respect to our integrated rate laws, we can go ahead and glean some information about our first order and second order half-lives. Okay, so basically we know that in a first order reaction, the concentration at a half-life is going to be half of the original concentration. So basically, we know that for every half-life that occurs, we'll have half of the previous amount of our reactant. So basically, this leads to this half-life equation here. So T1 half is equal to the natural log of 2 divided by our rate constant. Okay, obviously we don't have any concentration values inside our half-life equation for first order reaction, so the first order reaction half-life does not depend on the concentration. Okay, so it doesn't matter how much you have, basically a half-life will occur at the same time throughout the reaction progression. For second order half-lives, this is the half-life equation that we obtain. Notice that it does have a concentration value included in its equation. So unlike the first order reactions, the half-life for second order reactions do depend on the initial concentration of the reactants. And what this means is basically as your amount of initial concentration of your reactant changes, your half-life is going to change as the reaction proceeds. So basically the lower that initial concentration is, basically the longer the half-life. So the half-life is going to change as the reaction progresses for second order reactions. So in this problem here, they tell us that we have a reaction that is first order, and basically they want us to utilize the graph here to estimate the half-life and rate constant for this reaction. Okay, so we know it's first order, so we know we're going to utilize this equation. And basically they want us to figure out our half-life, and they want us to figure out our K value. Okay, so we're going to utilize this graph first in order to establish the point at which we have reached our first half-life. So the way we're going to do that is we're going to look at our initial concentration at time 0. So that's 0.100. Okay, so our first half-life, since this is a first order reaction, will occur when we have half of the original concentration. So that is going to occur here at 0.050 molar concentration. Okay, so we come across here and find the point where that value actually intersects with our graph. Okay, and that's going to occur at approximately 340 seconds. So our T1 half is going to equal 340 seconds. Okay, now obviously this is an estimation off of this graph, so there may be various numbers that people may estimate. Okay, however, you guys should be in some range that's pretty close to the 340 seconds. Okay, so now that we have our half-life, we're subsequently going to use that and the equation here to calculate our constant. Okay, so 340 seconds is going to equal to ln2 over k. Okay, so we want to have our rate constant all by itself. So what we're going to end up with is ln2 divided by 340 seconds. Okay, and if we plug this into our calculator, okay, this is going to give us 2.0 times 10 to the negative third, okay, inverse seconds, right, because we're dividing in that seconds unit. And that is our rate constant for this specific reaction. So as you can see, the rate laws and both differential and integrated allow us to find out specific information. The half-lives that are associated with these rate laws can also help us find specific information with respect to graphical data and things of that sort. So once again, making sure that we are relating the appropriate half-life equations to the appropriate order of the reaction and basically being able to utilize graphical data or just basically equation data and plugging it in and finding the variable that's missing is what we all need to be comfortable with. So organizing them in a way in which they all fall into the same category is what we all want to be working on.